Hey guys, today we're going to be covering some topics or formulas and equations that you will find in Module 5. So, you all are going to have to do quite a bit of memorization when it comes to some of these equations. So let's go ahead and try to go over these. So the first ones that you're going to have to deal with are percent by mass. So recall that this is simply a ratio, right? Percent by mass is going to be the grams of solute in a solution over grams of solute plus grams of solvent, right? And this portion down here is basically just your solution, right? The total amount of grams present in the solution. Now this ratio, because we want it in percentage form, it's going to be multiplied by 100. Okay, so take this for an example, right? Let's say we have a bowl of Captain Crunch. So let's say I have some red Captain Crunch here. I have some blue Captain Crunch cereals here. I have green Captain Crunch cereals, and I have purple. We can technically find the percent by mass for each of these different colors in the solution, right? So let's start with blue. I have 1, 2, 3, 4, 5. I have 5 grams of blue. Let's see how many total grams we have. So I still have the 5 grams of blue present, right? I'm also going to have the 1, 2, 3 grams, right? We have 3 green cereals there. I have 2 purple cereals. And then I have 1, 2, 3, 4, 5, 6 reds, right? So what's my total ratio here? Well, I have the 5 at the top. 6 plus 2 is 8, plus 5 plus 3 is 8, so it's 16. So that's my ratio, 5 divided by 16 times 100, right? So whatever that ratio ends up being would be my percent by mass for blue. I could do the same thing for green. Green would be 3 grams, and we now know that the total amount of grams in the solution are 16. So 3 divided by 16 times 100 would end up giving me my green percent by mass. Again, you can keep doing this for red. I have 6 grams of red. We know the total amount of grams in the solution is 16 times 100. That will give me my percent by mass for red, right? So if you were to apply this to a solution, each of these individual things would represent a molecule. And you just go about it like that. Same logic follows for molar ratio, right? Molar ratio is just finding the moles of A in a solution over the total amount of moles, right? So just like our cereal, grams over total amount of grams, we have moles of A over total moles of A, or in whatever solution A is. So for instance, let's say I have A2B turns into A and B. You have to make sure this is balanced, so there should be a 2 in front of that A. If I have 4 moles of A2B, right, all of it's going to get converted into 2A and 1B. So that means for every 1 mole of A, I form 2 moles of A, right? There's a ratio of 2 here. So if I have 4 moles of A, what's going to end up happening is I'm going to have 8 moles of A created, right? As opposed to B, I'll only have 4 moles of B created here, right? So if we were to find the molar ratio of A after this reaction, I have 8 moles of A divided by, well, the total amount of moles. Here I have 8 moles of A, right? Plus 4 moles of B. So my ratio here would be 8 divided by 12. This would be my molar ratio, right? So both of these are ratios. Just want to know how much of something we have in the entire solution. So the other types of equations you'll need to know, Here we have molarity. Molarity, often referred to as concentration or denoted by capital M, is your moles of solute over liters of solution, right? But again, we have to ask ourselves what a liter of solution is. Liters of solution is liters of solute plus liters of solvent, right? Now we move on to molality. So don't get molarity and molality confused. They're two different things. Ality, right? So we still have the amount of solute up here. However, the denominator is going to change. Now we're merely focusing on kilograms of solvent, right? That's because this is more focused on displacement rather than concentration. Molality is also denoted by like a lowercase cursive kind of m. And then lastly, we do have density, right? So if you remember from Chem 1, density or a broken heart is basically mass of solution, right, over volume of solution. So let's do our best to try to expand these types of equations, right? So what's my solution made up of? Your solute and your solvent, right? Mass is usually in grams, so grams of solute plus grams of solvent over volume is typically in milliliters for density, ml of solute over or plus ml of solvent. So a lot of times you'll be given some of the values for these equations. What you all will have to do is determine what kind of assumptions you are able to make according to what's given to you, right? So how do you discern what assumption you should make, right? So there's two different types of assumptions you can make, right? And some of them are best fit for certain conditions or based off of what's given to you in a problem. For instance, whenever you're given a percentage of sorts, it's best to make the assumption that you have 100 grams of your solution, right? 100 grams total of your solvent and your solute together. So that's the first assumption you can make. Second assumption, which you usually want to make whenever you're given molality, or density, will be you have 1 liter of your solution, right? So these are the types of assumptions you want to be making. Now, let's figure out what we have in common here. That's important because if you know one thing and assume another, you can implement that to other equations that we're talking about here, right? So for instance, let's say we know molarity, right? Molarity is moles of solute over the liters of your solution. What else has moles of solute here? Well, so does molality, right? Molality is moles of solute. And we know that moles to grams of solute is a very simple conversion. You just need to use the molar mass. So technically, your percent by mass up here also has grams of solute, right? At the top and at the bottom. And then when it comes to density, you also have moles of solute, right? Because like we said, moles of solute can be converted to grams of solute. So we know this portion here, right? So these are all essentially the same thing. Now, what else can we say? Well, percent by mass also has grams of solvent. What other part of another formula also contains grams of solvent? Well, if you go down to molality, kilograms of solvent, right? That's another simple conversion factor away, 1,000. What else? Well, the top part of density also has grams of solvent, right? So let's look at something else that these have in common. Let's look at liters of solute plus liters of solvent, or in other words, your liters of solution. Well, where else can we find that? If you look at density, that's the bottom portion, right? So let's just say, for instance, you make the assumption of 1 liter of solution, right? Where can I plug in that 1 liter of solution? I can technically plug that 1 liter solution at the bottom of molarity, 1 liter solution. I can also plug that in at the bottom of density, right? What's 1 liter of your solution in mLs? Because density needs to be in mLs. Basically 1,000 mLs, right? So if you're given molarity in a problem, let's say molarity was given to you and they tell you that it's 4.3, you technically know the amount of moles of solute that you have, right? If we know molarity is 4.3 and we're assuming 1 liter, then we can say we have 4.3 moles of solute. If we have 4.3 moles of solute, that can also be applied to molality, right? 4.3 moles of solute, right? And if molality is given, let's say molality was 8.6, how many kilograms of your solvent would you have? You'd technically have 0.5, right? So what I'm trying to get to is all of this connects with each other. You all have to fit the pieces of the puzzle and see what goes where.